Hi everyone, welcome to the talk of a PAC, Accelerating Smart Contract Vulnerability Detection via Parallel Fork Symbolic Execution. Our authors are from Science University and the Hong Kong Polytechnic University, and I'm Pelin Zheng. Okay, at the beginning of the presentation, I would like to talk about the background. As we all know, attacks on vulnerable smart contracts have resulted in severe financial loss. For example, SlowMix reported that the total amount of money lost due to blockchain attacks is over $20 billion, most of which are due to smart contract vulnerabilities. Hence, how to detect the vulnerability in smart contracts is attracting attention from academia and industry. There are substantial studies on detecting vulnerable smart contracts, especially the contracts running in Ethereum virtual machine, so-called EVM. They are based on various methods like symbolic execution, fuzzing, static analysis, and so on. As evaluated by smart bugs in ICSI, symbolic tools are effective. Here we give a survey on the tools of vulnerability detection for smart contracts based on symbolic execution, including the SE engine citations in Google Scholar and GitHub Forks. As for symbolic execution tool, ONT and Misreal are two popular tools from academia and industry. However, as evaluated by smart bugs, many symbolic tools for smart contracts are effective but cost much more time, as the symbolic tools need to traverse all potential paths to detect the vulnerabilities. Moreover, parallel SMT solving in those tools does not work well. We will test this later. So in this case, the coverage and accuracy of the symbolic tools are limited by the time. One more thing is that existing parallel SE solution cannot be applied to smart contract. There are several studies on parallel symbolic execution for improving the performance, such as Cloud9, Parsim, Score, PASI, and Parallel JPF. However, they cannot be applied to detecting vulnerabilities in smart contracts for the following reasons. Reason one is lack of global view of all paths. Previous studies lack a global view of the whole symbolic execution tree, which is not needed in their scenarios, because their major target is to generate test cases for traditional programs, and those test cases are enough to trigger the traditional bugs, such as index out of bound in the array. Okay, so in smart contracts are different from traditional programs. In a smart contract, the execution of two non-buggy paths may still result in an exploitable bug, such as the transaction ordering bugs. Hence, for those vulnerability patterns depending on the global variables during the symbolic execution of contracts, previous studies cannot work. Reason 2 is no EVM state copy solution. A smart contract can be triggered by a series of transactions, of which the states should be copied among parallel units. However, previous studies do not deliver the state copy among the units. Instead, they deliver the replay or prefix paths. The replay or prefix solution is oriented to deliver symbolic paths through network transmission, but it will cause redundant computing. Moreover, the replay or prefix implementation is deeply coupled with their target programs and cannot be directly migrated to EVM-based smart contract. So before introducing our design, I would like to introduce two basic concepts. First, symbolic execution has been used to detect vulnerabilities in smart contracts. The first figure shows that the code of the smart contract can be conducted as a symbolic execution tree. There are two symbols, X and Y, affecting the execution path. As shown in the second figure in the middle, the variables in blue and green are generated symbols in the symbolic execution of an EVM smart contract, including X and Y in the first figure. Okay, after the tool traverses all the paths, it can detect vulnerabilities by matching the patterns. Second, in Unix-like operating system, one way to create a new process is to use the fork from the operating system. As shown in the third figure, once A uses fork to create process B, B has an independent memory space. Unix-like operating system applies the copy-to-write feature at that moment. Hence, at the moment, the OS does not copy the physical memory, and A and B have independent memory space by using the same physical memory. Only when B changes the memory, the new physical memory is allocated and written. Note that this copy-to-write feature will be used as the communication of PARC. Next, we will introduce the design of PARC. To address the above-mentioned issues, we propose PARC, a general framework for parallel fork symbolic execution for smart contracts. Fork refers to the fork in the symbolic execution tree and also the process management. PARC leverages multiple CPU cores to explore different symbolic paths in parallel in order to shorten the execution time and provide higher coverage of the code. An example of PARC symbolic execution of an EVM-based smart contract is shown in this figure. As you can see, the total execution tree in the left is divided into 3 processes on the right. Okay, each process holds partial path forks of the EVM contract. Hence, the time can be shortened. To the best of our knowledge, PARC is the first study that provides parallel symbolic execution for smart contracts. For ease of explanation, we present an example workflow in PARC as shown in this figure. The symbolic execution tree is shown in the left, right, and in the right, there are 3 CPU cores. In this example, we omit the process switching between CPU cores. So in the beginning, process 1 executes code A and code B in serial. When it finishes B, it faces 2 forks, also called branches, in the control flow graph, okay, just C and D. At this moment, PARC fork the process to process 2 to execute D, and process 1 goes for C. Note that process 2 will hold the information of A and B as its memory is the same as process 1. So the same thing goes on in process 3 for code E and code F, okay? These 3 processes run on different CPU cores and serialize the global variables to the shared memory of PARC. Finally, process 1 reconstructs the global variables and detects the vulnerabilities. In this example, the original execution will be executing 6 codes on a CPU core. With PARC, the single CPU core only executes partial of the codes, thus the time is shortened. To implement this main idea, we still need to tackle 3 technical challenges as follows. Challenge 1 is how to partition the symbolic execution tree and copy the states of EVM-based contracts. The challenge 2 is how to avoid the performance loss of SMT solver on multiple CPU cores. The challenge 3 is how to maintain the global variables of different forks for detecting vulnerabilities, as mentioned in reason 1. We propose new solutions to address these challenges. The architecture of PARC is as follows. The fork operation-based dynamic forking is a module to decide where to fork and the process and copy the EVM state. It is exposed as an interface used to check the information given by the symbolic EVM. The adaptive processes restriction and adjustment is a module to evaluate how many processes are proper on the exact CPU. In the meanwhile, it will reduce the effects of the SMT performance loss problem by adjusting the SMT timeout. The global variable reconstruction is a module to collect and reconstruct the global variables among several symbolic engines for vulnerability detection. Note that the symbolic EVM and main process and the detecting modules are from the original tools, such as ONT and Misreal. So the 3 modules on the top of the figure are from PARC. Based on the above modules in PARC, the steps are described as follows. First, the EVM contract is input into the symbolic EVM, and then the symbolic EVM executes the contract. After that, the symbolic EVM will synchronize its status to the forking manager, just this module. Okay, with the decision made by PARC, the forking manager will call the operating system to fork the process if needed. After that, it returns the branches that they should go next to the symbolic EVM. And the fourth step is that as for the EVMs in parallel processes, PARC will use the second module to adjust the timeout of SMT solvers. The 5th step is to collect the global variables. Once a symbolic EVM finishes its execution, its output will be redirected to the shared memory. and all the global variables that are related to the vulnerabilities will be serialized into the memory. The process waiting means that once the main process finishes its work before other, it will wait for other child processes to be finished. After that, it will reconstruct the global variables, and finally, it can detect the vulnerabilities and report them to the file as its original way. Okay, the benefits brought by Park corresponds to our goals. First is shortening the time, and second, it will ensure the same detected result. And finally, this is a decoupled architecture to make it easier to support other applications. Next, we will show the detailed design of Park. First is the fork operation-based dynamic forking. It accepts the inputs as opcode, state, and constraints, and it outputs the process signal to the processes. If you want to know the detailed algorithm, please refer to our paper. And the adaptive process restriction and adjustment is going to solve the SMT performance loss problem. As you can see in the left figure, when we run more processes at the same time, the solving time for the same SMT is longer. So we need to benchmark the CPU first, and then we will get the parameter of restriction and adjustment. Third is the shared memory-based global variable reconstruction. This is the necessity of global variables. As you can see in this table, there are 4 vulnerabilities, and 2 of them need the global variable as the key symbols. And so we design 4 variable types to reconstruct them. Next, we will show the experiment of Park. Park is implemented as a plugin applied onto ONT and Misreal. We use 2 third-party datasets from Smartbox and Export-ATH for evaluation. One consists of 142 labeled smart contracts, and the other consists of 1,000 most triggered real-world contracts. As for research question 1, we find that original parallel SMT solving in ONT and Misreal does not work well on multiple CPU cores, so it cannot improve the performance very well. As for the research question 2, we will evaluate the improvement in vulnerability detection. We find that on the Smartbox dataset, with the same true positives, Park can provide 6.84 speedup for ONT and 7.06 speedup for Misreal. Okay, and on the other dataset, that is the top 1K dataset, Park-based tools also cost less time. You can see that for the original full contracts, it can provide 7.26 speedup for ONT and 7.86 for speedup for Misreal, and it also detects more positives than the original tool. If we look into the last test group, we can list each speedup for each contract. We can find that Park accelerates most contracts and decreases performance for only very few ones. For research question 3, we will find the impact of parameters. First is the CPU cost. Despite the impact on the CPU power war, in most cases, Park can achieve higher coverage with more CPU cores, hence detecting more vulnerabilities. And we also find that in most cases, as the global timeout increases, so does the number of detected vulnerabilities and coverage. This can be used in other evaluation of the symbolic tools for the smart contracts. Okay, finally is the conclusion. This paper presents a framework of Park parallel fork symbolic execution, and it introduces a fork operation-based dynamic forking algorithm. It also proposes an adaptive processes restriction and adjustment algorithm. It uses a shared memory-based global variable reconstruction method to maintain the consistency. As for the future work, there are some other parameters in Park and the original tools that need to be investigated, and the adjustment of solver timeout has some random effects. So recently, inspired by the Z3 solver, we will use the R-limit rather than the timeout to solve the challenge 2, and it can achieve higher consistencies, but sometimes it costs more time. Okay, and finally, the forking is still too heavy for the OS scheduling. That can be solved in the future work. So next is 2 websites of this project and our labs. Finally, we would like to thank to all the reviewers and all the researchers who have participated in the discussion. Thank you.